Hello everyone. In this lecture, we are deriving a relationship between critical constants and van der Waals constants. We know the van der Waals equation for 1 mole of a gas is P plus A by V square into V minus B equal to RT. Expanding this, we will get PV minus PB plus A by V minus AB by V square minus RT equal to 0. I am multiplying this by V square by P so that the new equation becomes V cube minus of B plus RT by P into V square plus A by P into V minus AB by P equal to 0. Here also now you take a paper or a book and try to derive this along with my lecture so that it may be easy to be handled. This is a cubic equation in the variable V, and therefore as it is a cubic equation, for any single set of values of P and T there should be 3 values for V. If at a constant temperature the values of V are plotted against P, then according to this equation we will get some lines like this. It will be seen readily that for a certain pressure there are 3 values of V marked. I am marking it for the first line as A, B and C. As the temperature increases from 0, 13, 21, etc., the isotherm moves up and the 3 values get closer and closer to one another. At a certain temperature, the 3 values of V, here is the isotherm, in the 4th isotherm, the 3 values of V become identical as shown by the point X. At a still higher temperature, there is only one real value of V corresponding to given pressure. Thus, below the critical temperature of a gas, the isotherm indicates 3 values of V for a given pressure in accordance with the above equation. It also may be pointed out that the isotherms plotted in this figure are based on theoretical calculations of V corresponding to different values of P obtained by using van der Waals equation. The isotherms for carbon dioxide obtained by Andrews experimentally were in close resemblance with these curves that we have discussed earlier, and you can realize the close resemblance. There is only one difference, that the wave-like portion here was replaced by a horizontal line in the experimental isotherm. Since then, more careful experiments have shown that small portions corresponding to the curves, the crest and troughs here, can be realized in practice also. Experimentally also, these represent supersaturated vapor and supersaturated liquid respectively. As the temperature is raised, we have seen the loops become smaller and smaller, as already stated. And at the critical point X, you can see the temperature is nearly 31 degrees Celsius as the critical temperature. All the 3 values of V becomes identical. Since the temperature is now critical, this value of V represents the critical volume of the gas. Thus, V become equal to Vc. So we can write V minus Vc the whole cube equal to 0. Expanding and writing in decreasing powers of V, you can get V cube minus 3Vc into V square plus 3Vc square into V minus Vc cube equal to 0. This equation is identical with the van der Waals equation at critical temperature and pressure, which we have derived earlier, and if we represent the PC and the TC at critical temperature and pressure, we will get these two equations identical. As they are identical, the coefficients of equal powers of V can be equated, so that you can easily write as what the coefficient of V square, you equate 3Vc become equal to V plus RTC by PC. Then I'm giving equation as 1. Then next 3Vc square become A by PC, and the constant Vc cube equal to AB by PC. You get 3 equations. From these 3 equations, the critical constants Tc, Pc and Vc of a gas can be calculated in terms of van der Waals constants A and B. Like this, if we divide the equation 3 by equation 2, we will get Vc equal to 3B. Then, substituting this value of Vc in the second equation, we will get Pc equal to A by 27B square. This is that I said earlier that you write it along with my lecture, so that it become more easier for you. And inserting this value of Vc and Pc in the first equation, we will get Tc becomes 8A by 27Rb. Thus, knowing the critical constants of a gas, it is possible to calculate the van der Waals constants and vice versa. By this, we are coming to the end of this chapter, and we have some other simple portions that I will distribute you for seminars. And thank you very much all.